Let's explore what photodiodes are, how they work, and where they're useful. So photodiodes are a class of diodes that convert light to electricity. They convert light to electricity. And they are the exact opposite. Their working is also exact opposite of LEDs. You may have heard of LEDs, which are like tiny bulbs. They convert electricity to light. They're also diodes, but they do the exact opposite. Now, when you hear light being converted to electricity, the first thing that comes to my mind at least is solar panels, right? So photodiodes definitely are used in solar panels, but those are specifically called solar cells, and we'll talk about them in a future video. Over here, when we say photodiodes, we're talking about a bunch of diodes whose major application is in detecting the brightness of light. So let me just write that down. They're used in detecting the brightness of the light that is shining on them. So let's see how that works. So since these are diodes, we'll start with the PN junction. So take a PN junction, and to make it detect the brightness of light, you have to reverse bias it. And this is super important. And we'll see in a while why reverse bias, why not forward bias. We'll look at that in detail, but you have to reverse bias your PN junction. So let's do that. Let's take our PN junction and reverse bias it. What do we mean by reverse biasing? Well, biasing means attaching a battery. Reverse biasing means making sure that the P side is connected to the negative and the N side is connected to the positive. This is called the reverse bias. And of course, you'll always have some resistor to limit the current, making sure that the diode doesn't get destroyed. And so this is the circuit for our photodiode. So let's start by thinking about what happens before we shine light on it. This is something that we've already seen before, but let's quickly recap. We know that a PN junction contains holes, P side contains holes, and N side contains electrons. And then there is a region in between which has no holes or electrons, but only contains this space charge. We call this the depletion region. And the depletion region acts like a barrier for the holes and electrons to diffuse into each other. For example, if the electron tries to come here, it gets repelled by this negative and goes back. If the hole tries to come here, it gets repelled by this positive and tries to go back. And when you reverse bias it, because the holes are attracted away and the electrons are also attracted away from, towards the positive charge, away from the depletion region becomes wider, the barrier becomes larger. And so it becomes further difficult for electrons and holes to diffuse into each other. And we've talked about this in great detail in previous videos on reverse current and forward current of PN junctions. So if you need more clarity, then feel free to go back and check that out. But now let's think about what happens when we shine light. So let's say we shine light over here. What's gonna happen? Well, for this, we need to go back to our band theory of solids. You might recall that semiconductors have at the topmost level two bands, the conduction band and the valency band. And if you look at the depletion region, we are seeing no charge carriers, which means the conduction band is empty because the free electrons are supposed to be in the conduction band. And the valency band is completely filled with electrons, which means there can be no conduction. And that's the reason there are no charge carriers over here. This is the picture. But what happens when you shine light? Well, when you shine light, if the photons of light have sufficient amount of energy, energy more than this band gap, then some of these electrons can absorb that and jump into the conduction band. And now as a result, notice we have a free electron and we have a free hole. Now, if this were to happen somewhere over here outside the depletion region, then a little later, the electron and the hole will recombine and nothing special would happen. But when this happens at the depletion region, look at what happens. So let's say the electron hole pair is formed somewhere in the depletion region. Let me zoom in. Okay, so somewhere over here, let's say here is our electron. Oops, here is our electron and here is that hole. Now, before they have a chance to recombine, this electron will get attracted by this positive charge and repelled by this negative charge, and as a result, it'll accelerate in this direction. And this hole, similarly, will be attracted by this, repelled by this, and will get accelerated in this direction. And as a result, notice we now are having a current, right? Holes moving this way or electrons moving this way will give us a current towards the left. And so there will be a current in this circuit due to the electron holes generated due to the light. So let me zoom back. And that's how, due to light, we get a current. Okay, now imagine we were to shine more light or brighter light. That's what I meant, okay. Brighter light. What's gonna happen? What do you think will happen to the current? Can you pause the video and think a little bit about what's gonna happen? All right, if there is a brighter light, that means there are more photons being absorbed per second. Means more electron hole pairs will be formed per second, and therefore your current will increase. Ooh, so notice, with more light, we get more current, which means just by looking at the current, I can now tell how bright the light is. And there you go, photodiodes. They are detecting the brightness by using reverse bias. More current means more brightness. All right, now before we go forward, an important question to address: why reverse bias? Why not forward bias? And I want you to take a crack at this first. Can you pause the video and think a little bit about this? And I'll give you a clue. It's got something to do with the depletion region. So pause and give it a shot. All right, hopefully you've tried. Remember, if you want that photon to generate electron hole pair which contributes to the current, that has to be formed in the depletion region. Otherwise, they will just recombine and they will not contribute to the current, which means that photon's effect will be useless. So what happens when you forward bias? You may have already studied that when you forward bias, the depletion region becomes narrower. So let me just show you that. If the depletion region narrows, then notice the electron hole pair which are formed have now less chances of being formed in the depletion region. And as a result, most of the photons which are absorbed will be useless. They will not be contributing to the current. And it's for that reason we use a reverse bias, so that we have a nice and large depletion region. And so a lot of photons will contribute to the current. Does that make sense? And of course, another important reason is in the forward bias, because the depletion region has now become smaller, these holes and electrons will also start diffusing and start causing a current. And that will mess with our calculations. Remember, we want the current only due to the light because we are detecting the light. That's our whole idea, right? So to make sure we don't have any other currents, and to make sure that we have a large enough depletion region, that's why we are making sure photodiodes work in the reverse bias. Finally, let's talk about its applications. Where is this useful? Before we do that, it'll be easier to do that if we draw a VI characteristics. So let's go ahead and do that. Let's draw the voltage versus current characteristics. And again, this is something that we've already seen before. It's a reverse bias characteristic. So why don't you pause the video and try drawing this characteristics yourself. All right, let's see. Because the voltage is reverse biased over here, we'll get the negative voltage. And because the current is from N to P, notice it's from N to P, that current will also be negative. And therefore, we're gonna get our graph in this region, the third quadrant. And what would the graph look like? Well, just like the normal reverse bias graph, it's gonna look somewhat like this. So what is the graph saying? Well, the graph is saying that the current generated is pretty much independent of the voltage after a particular point. Why is that? Well, the reason is the current generated depends on the light, right? Depending upon amount of light, you have a certain amount of electron hole pairs being formed, and those electron hole pairs are being captured. So if there are 10 electron hole pairs being captured per second, then your current will be just that. And it has nothing to do with the voltage. Even if you increase the voltage, the number of electron hole pairs formed would be the same. And that's why pretty much it is independent of the voltage. But of course it does depend a little bit, because if you increase the voltage, the depletion region widens a little bit, and therefore more chances of electron hole pairs being formed in the depletion region. But pretty much it is independent of it. Now what happens if you increase light? Well, so let's say this is with some amount of light. What happens if you put more light? What would this graph look like? Well, with more light, the graph will be similar, but we'll have more current in the negative direction. And therefore your graph might look somewhat like this now. This is with more light. and so on and so forth. Even more light if you put, look like this. This is even more light and so on, okay? And again, notice the current level is telling me how much light is falling on my diode. But one thing to remember is that even in the absence of light, there is thermal energy, and the thermal energy also causes electron-hole pairs to be formed. So even in the absence of light, you will get a very tiny amount of current, which I'm gonna draw somewhere over here. We usually call this the dark current. So even though you're not shining light purposely, there is background thermal radiation that causes this as well. So where would we use this? Well, this would be useful in automatically switching things from light. For example, you can attach this circuit to an automatic street light, and you can build that in such a way that if the current is below a certain level, meaning it's very dark, then you switch on that street light. If the current is above a certain level, which means there's a lot of light, you switch off that street light. Beautiful, isn't it? Let me give you another example. You must have seen note counters in the bank. One of the ways we can do that is again by using a photodiode and shining a laser on it. Whenever there is a laser shining on it, because of light, there will be a high current. But every time a note cuts that laser as it moves, the current goes down and comes back up. And you build a circuit which just counts, adds a +1 every time a current drops and comes back up. So by using lasers, LEDs, and photodiodes, we can do a lot of wonderful stuff.